Hello everyone. In the last video, we talked about how to build a synchronous irregular counter by using different type of flip-flop, and we have used the flip-flop to build our counter. So in this video, I will use the T flip-flop to build our synchronous irregular counter. So basically everything is the same. We are using the same sequences in last video, so this tool is basically the same, and the only difference here is the input of the flip-flop. So as we can see, we are using T flip-flop, so we refer the excitation table of T flip-flop here. Okay, so now we determine its input. So for the first one, for T1, we see the first column. As we say in last video, we see the first column for T1. Okay, so this is present state 0 to next state 1. So we see here present state 0, next state 1, and then we get 1. So here we write 1. And then you determine the other else, and then we determine the input of T2. And T2, of course, we are looking at the second column. Okay, so for the second column is also 0 to 1. Okay, excitation table 0 to 1 is 1. So 0 is 1. And then we do the same for other rows. And then for T3, we're looking at the third column. Okay, so the present state 0, present state 0. To next state is also 0. So we look at the excitation table. Present state 0, next state 0. Sorry, wrong table. This one. Uh, present state 0, next state 0, and then we get 0 input. So here we write 0. Yeah. And then we do the same for other sequences. And then you will get this result. After that, we do the care map. So in last video, we already talked about how to do the care map. Okay, you just refer to the present states. Okay, this is Q1, this is Q2, and then this is Q3. So this is Q1, this is Q2, and this is Q3. Okay, so you just refer the present state. Okay, for an example, the first one 0 0 0. For T1 is 1. So for T1, the care map of T1 0 0 0 is 1, and then you do all for the other sequences, so we can get the Boolean expression of T1 equals to Q2 bar. Because why? Because you see Q3, the input of Q3 change, so you can ignore it. And then you see Q1, the input also change, so you can also ignore it, but Q2 doesn't change. And then you see both are 0, both are low input, so you add a bar here, so it's T1 equals to Q2 bar. And then for T2 we get 1 because everything can be grouped together, so T2 equals 1. T3 equals 0 because there's nothing to group with, so T2 equals to T3 equals to 0. And then we can build our circuit. So this is our circuit. This is the circuit for our T flip-flop synchronous irregular counter. So the T flip-flop is very easy. Okay, as we see T1 equals to Q2. So this is T1, this is T1, this is T2, and this is T3. So T1 here is equals to Q2 bar. So this is Q2 bar. This is, let me enlarge for you. This is Q2 bar. So you link the Q2 bar to T1. And then we see here T2 equal 1. So T2 you connect to a power source. 1, and then T3 equal to 0. So in here T3 you don't need to connect anything to the T3 inputs, and then we can simulate our simulation. We can simulate our circuit. 0, 6, 4, 2, 0, 6, 4, 2, and this proof that we can our synchronous irregular counter is succeed. Okay, so for the next example I will use JK flip-flop to build our synchronized irregular counter. So for JK flip-flop is this one. Okay, the only difference of JK flip-flop and D and T flip-flop is JK flip-flop you need to separate its K map. Okay, like J1 you need one K map, and then K1 you need one K map. So D and T flip-flop you have like 3 K map, but JK flip-flop you need to like double the K map. Okay, for example we see the present state. Okay, we see the present state and then we compare with the next state. Okay, so we are using JK flip-flop. We're comparing it with the excitation of JK flip-flop here. So for the first one example, J1 K1 is first row. So we see the first row. So first column, sorry. So in the present state is 0, next state is 1. So we see J first. Okay, so 0 to 1 equals to 1. So the J will become 1. And Y here is X. This X is for the K. You see the K is X. So X. 0 to 1 is equals to 1x, so 1x. So for the next sequence is 0 to 0. Okay, so we look at the excitation table. 0 to 0 is 0x. So we write here 0x. Okay, so for the K map, also you see the present state. Okay, for example 0, 0, 0 is equal to 1x. Okay, so 0, 0, 0 is equal to, okay, so this is the K map for J1. So you only see J, you don't see the K, you only see J, you only see the first number. Okay, like this one the first number is 1, so you just see the first number. So 0, 0, 0 is 1, so 0, 0, 0 is 1. Okay, and the K map here, so for K1 is 0, 0, 0 is X, so 0, 0, 0 is X. So and then you do the same for the other K maps, and then we can get the Boolean expression of J1 equals to Q2 bar, K1 equals to Q2 bar, J2 equals to 1, K2 also equals to 1, J3 and K3 both equals to 0, and then we start to build our circuit. So this is the JK flip-flop, like a irregular counter by JK flip-flop, the circuit of it. Okay, first we see J1 equals to Q2 bar. Let me enlarge. J1 equals to Q2 bar. So this is Q2 bar, this is J1, you connect it. And then K1 also equal to Q2 bar. So K1, Q2 bar, connect together. Easy. So J2 and K2 both equal 1. So J2 and K2 connected to the source. And then J3 and K3 equal to 0. So you don't need to connect anything for J3 and K3. Okay. So let's simulate our circuit to see if we are wrong or right. So 0, 6, 4, 2.